Yeah, and then we can enter a new topic. We enter the sum of divisor function, which denotes as sigma n little sigma n. This function is very similar. It's also multiplicative, and we can also write, and it's easy if if we only consider uh, the n that n is a prime power. It's very easy because it's like all the divisors are the prime power and all over to pk, and we know this is a geometric progression, and we get the function, the formula of a single power prime powers sum of divisors. If we know that this is the multiplicative, we know for n, if n is equal to the product of each prime numbers, we know that like the sum of divisors of n would be like every each kind of such expression times together. The first is p1, second is p2, sorry, p1, p2, p2 alpha 2 plus 1 all over to pk plus minus 1 the pk alpha k plus 1 minus 1. That's how we find our formula, but the thing is we need to prove this is multiplicative. But another way is that we can directly deduce that the sum of divisors kind of multiplicative. Our insight comes from we can kind of write a table like this: p sorry p square p cube p to the power of 4. If we, for example, n is equal to p to the power of 4 times q to the power of 2, we can like directly list this form, and it represents every number, every divisors for n. We time them together like this: qp square qp cubed qp4 to the power of 4. And in general, we see that it's kind of what we are essentially doing is that expanding this two functions is this to geometric progression, right? And that's essentially the the sum of divisors of q square, and this is the sum of divisors of p to the power of 4. And essentially you can kind of try to generalize this and write down the kind of the multiplicative proof, and the inside is you can see this form. Yeah, very clear. And we can also like we now enter a new function. It's called the phi function, or phi n, or Euler's totient function. This function, as we've mentioned in the earlier session, we've mentioned that given an A and N which they are co-prime, we got A phi N is modulo 1 mod N is congruent to 1 mod N. And this expression gives us the number of the number of number that is co-prime with N in the interval 1 to N minus 1. In this interval, how many 1 to N minus 1? In this interval, how many numbers are co-prime with N? For example, for 15, the number less than 15 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And for 15, 1 is co-prime with 15, 2 is, 3 is not, 4 is, 5 is not, 6 is not, 7 is, 8 is, 9 is not, co-prime 3, 10 is not, 11 is, 12 isn't because it's co-prime with 3, 13 is, 14 is, 1, 2, 3, 4, 5, 6, 7. So 15 is equal to 7. Similarly, how can the general equation or the general formula of phi n is that we, for each prime p to the power of k, we pi to the power of alpha I, we times 1 minus pi 1 over pi, because in general in the first 15 integers, the number that co-prime with 3 occurs, or that is not co-prime with 3 occurs like once every 3 times, 3 integers. Like number co-prime with 3 is 3's multiple, which occurs every 3 times. So we have to delete those numbers, which is 1 over 3. We times 1 over 3 to we minus 1 over 3 from the whole 15 integers. So we got the general equation like this, and we can add we can sum every prime. Yeah, we can sum every prime, and this is what essentially we are looking for, and we can also easily prove that phi n is also multiplicative, because it's definitely multiplicative, because from this equation we directly notice that it is the same as the sum of phi p I alpha I, right? And this indicates that it's the phi n is multiplicative, and then we know that phi n is multiplicative. All those today's going to our functions are all multiplicative. Yeah, the multiplicative is very powerful because as long as we know the equation of a single prime factor, as long as, for example, we know the function of p's power, we can generalize to the whole every natural number n. Yeah. And next we can talk about an interesting lemma from Gauss. Talk about the lemma. We prove that this summation is equal to n. What it essentially means that is that, for example, 15, we sum it, we write down its every divisors, the Euler's totient function. For example, it's phi 1 plus phi 3 plus phi 5 plus phi 15, and this expression should be equal to 15 itself. Very interesting, right? We can have some check. Phi 1 is equal to 1, phi 3 equal to 2, phi 5 equal to 4, and phi 15, as we've mentioned, let's have some check, is equal to what? Phi 15 is equal to 7, right? 1 plus 2 plus 4 plus, this should be this should be equal to 8. Sorry, I think I've made some mistake, and this is 15. And what how can we prove this? You can think about it. It's sometimes because we know the general formula of phi n, we may kind of prove it algebraically, right? Algebraically, we have mu d is equal to p. When similarly we denote n equals p1 alpha 1 pk times to pk alpha k, and phi d, for example, is a kind of if d should like p beta e over to pk beta k, where each beta alpha I is greater or equal to beta y, right? And we can write phi d as p1 beta 1 minus p1 beta 1 minus 1 over to pk as our general formula tells us. And the thing is that because here we can kind of simplify this problem through multiplicative property, right? Multiplicative is a very good property. We can simplify many things by it. And through it, we know that because if we can prove that if n is pk, if we can prove this formula, we can prove the formula for every n, right? But why is that true? Is we can directly time, for example, if n is many primes, we can times it together, and it's kind of time that multiplicative table, right? 1p as you've remembered, as we've talked about. And this is essentially the same idea. Yeah, that's how we can simplify this problem to pk. Only consider the saturation of pk. When it's pk, it's kind of quite simple to show, because we know that the pk for all the divisors of pk are 1 to p square all over to pk, right? And we write the Euler's totient function of this together, we kind of get a sorry, there's a mosquito and we kind of very annoying, and we kind of get 1 p square. Sorry, there's an n. Wow, this n is can't die. And over to pk, as we've written the formula as kind of this form. It's very easy to telescope it. It's like 1 minus 0, p minus 1, plus p2 minus p, plus all over to pk minus p. And that's essentially pk. We telescope them, and we get finally pk is left. And we know that it's what we prove is that for pk, the sum is equal to pk, and as a result we know it's multiplicative, and we generalize, we get that it's true for every n. Yeah, and we finished our proof. Some part of them might not be very rigor, but you can prove it anyway. You have that insight, and it's easy to prove. Yeah, and we can I will leave you some problem to think about. For example, you can think about also we need some bond of run, right? You can think about this. You can think about the lower bound. This is greater than square root of n. You can think about it. Yeah, that's we finished our discussion of Euler's totient function.